Bonding the conduit to the utility neutral will provide a low-resistance path for fault currents to return to the source. This action prevents high voltages from building up in the conduit, thereby reducing the risk of touch voltage. The utility neutral bonding shouldn't trip the primary cutouts. These cutouts are specifically designed to protect the primary circuit from overcurrents. They operate by opening when the current surpasses a predetermined threshold. Importantly, bonding the conduit to the neutral does not increase the current flow in the primary circuit, so it should not activate the cutouts. To further mitigate the risk of touch voltage, several measures should be implemented. Firstly, ensure that the conduit is properly grounded to the utility neutral. Secondly, conduct regular inspections of the conduit to check for any signs of damage or corrosion that could potentially compromise the integrity of the bond. Thirdly, always utilize insulated gloves when performing any work on or in proximity to the conduit. Fourthly, strategically place warning signs to effectively alert both workers and the general public to the possible hazards present. Ground rods alone are generally not adequate for creating a dependable low-resistance pathway for fault currents. This limitation primarily stems from the fact that ground rods typically exhibit a high level of resistance to the earth, especially when the surrounding soil is dry or frozen. As such, bonding to the utility neutral offers a more effective and reliable return path for fault currents. Electrical bonding is the process of intentionally connecting metallic parts of an electrical installation that are not intended to carry current. This connection creates a low impedance path for fault current, facilitating the operation of overcurrent protective devices like circuit breakers or fuses, and minimizing the risk of electric shock. There are several key reasons why bonding is essential for electrical safety. Firstly, bonding reduces touch voltage. In the event of a fault, such as a live wire coming into contact with a metallic enclosure, the voltage potential of the enclosure will rise. Bonding ensures that all metallic parts are at or near the same potential, minimizing the voltage difference between them and the ground. This significantly reduces the risk of electric shock if a person comes into contact with a faulted enclosure. Secondly, bonding facilitates the operation of overcurrent protection. A low impedance bonding path allows a large fault current to flow quickly back to the source. This high current will trip the circuit breaker or blow the fuse, rapidly disconnecting the faulted circuit and preventing further damage or injury. Thirdly, bonding minimizes electromagnetic interference. Bonding can help to reduce electromagnetic interference by providing a path for unwanted currents to flow back to the source. This can improve the performance of sensitive electronic equipment. Several types of bonding are commonly used in electrical installations. Firstly, equipment bonding connects non-current carrying metal parts of equipment, such as enclosures, raceways, and frames, to the grounding electrode system. This ensures that these parts are at or near ground potential. Secondly, main bonding jumper connects the grounded conductor neutral to the equipment grounding conductor at the service entrance. This provides the primary path for fault current to return to the source. Thirdly, supplemental bonding connects different metallic parts together to ensure that they are at the same potential. This is often used in areas where there is a high risk of electric shock, such as swimming pools or hospitals. Several key requirements must be met to ensure effective bonding. Firstly, all bonding connections must be mechanically sound and electrically continuous. This means that the connections must be tight, corrosion-resistant, and able to withstand the stresses of normal use. Secondly, bonding conductors must be sized appropriately for the fault current they are expected to carry. The size of the bonding conductor is typically determined by the size of the overcurrent protective device protecting the circuit. Thirdly, bonding conductors must be installed in a manner that minimizes impedance. This means that the conductors should be as short and straight as possible and should avoid sharp bends or loops. Grounding, on the other hand, refers to the connection of an electrical system or equipment to the earth. This provides a reference point for voltage and helps to stabilize the electrical system. Grounding also provides a path for fault current to flow back to the source, but it is not as effective as bonding in clearing faults. There are several key reasons why grounding is important. Firstly, grounding stabilizes voltage. Connecting an electrical system to ground provides a reference point for voltage, preventing voltage fluctuations and ensuring that the system operates properly. Secondly, grounding provides a path for fault current. In the event of a fault, grounding provides a path for fault current to flow back to the source. This helps to protect people and equipment from electric shock. Thirdly, grounding protects against lightning strikes. Grounding can help to protect electrical systems and equipment from damage caused by lightning strikes. Several types of grounding are commonly used. Firstly, system grounding connects the neutral point of a power system to ground. This is typically done at the service entrance. Secondly, equipment grounding connects the non-current carrying metal parts of equipment to ground. This is done to protect people from electric shock. Thirdly, electrode grounding connects the grounding electrode system to ground. This provides a low impedance path for fault current to flow back to the source. Several key requirements must be met to ensure effective grounding. Firstly, the grounding electrode system must be properly installed. This typically involves driving one or more ground rods into the earth. Secondly, the grounding electrode system must have a low impedance connection to ground. This means that the resistance between the grounding electrode system and the earth must be low. Thirdly, the grounding electrode system must be protected from damage. This can be done by enclosing the grounding electrode system in a protective enclosure. Now let's discuss the specific situation of bonding conduit to the utility neutral. This practice is commonly used to ensure the safety of electrical systems, particularly in situations where the conduit may become energized due to a fault. The utility neutral is the grounded conductor of the electrical supply system. It is connected to the earth at the transformer and at the service entrance. By bonding the conduit to the utility neutral, you are providing a lower impedance path for fault current to flow back to the source. This will help to trip the circuit breaker or blow the fuse in the event of a fault, protecting people and equipment from electric shock. There are several benefits to bonding conduit to the utility neutral. Firstly, it reduces the risk of electric shock. By providing a low impedance path for fault current, bonding helps to quickly clear faults and prevent dangerous voltages from appearing on the conduit. Secondly, it protects equipment from damage. By quickly clearing faults, bonding helps to prevent damage to electrical equipment. Thirdly, it improves the reliability of the electrical system. By providing a stable ground reference, bonding helps to improve the reliability of the electrical system. There are also some potential drawbacks to bonding conduit to the utility neutral. Firstly, it can increase the risk of ground loops. Ground loops can occur when there are multiple ground paths in an electrical system. This can cause unwanted currents to flow through the ground conductors, which can interfere with the operation of sensitive electronic equipment. Secondly, it can make it more difficult to troubleshoot electrical problems. When the conduit is bonded to the utility neutral, it can be difficult to isolate faults. This is because the fault current can flow through multiple paths. To minimize the potential drawbacks of bonding conduit to the utility neutral, it is important to follow proper installation practices. Firstly, use the correct size bonding conductor. The size of the bonding conductor should be determined by the size of the overcurrent protective device protecting the circuit. Secondly, make sure the bonding connections are mechanically sound and electrically continuous. The connections should be tight, corrosion-resistant, and able to withstand the stresses of normal use. Thirdly, avoid creating ground loops. This can be done by using a single-point grounding system. Fourthly, properly document the bonding connections. This will make it easier to troubleshoot electrical problems in the future. Ground rods alone are not sufficient to provide a low impedance path for fault current. Ground rods have a relatively high resistance to earth, especially in dry or frozen soil. This means that it will take longer for the fault current to flow back to the source, which increases the risk of electric shock and equipment damage. In addition, ground rods do not provide a stable ground reference. This can cause voltage fluctuations and interfere with the operation of sensitive electronic equipment. For these reasons, it is important to bond the conduit to the utility neutral in addition to using ground rods. The bonding connection will provide a low impedance path for fault current and a stable ground reference. Here are some additional safety measures to take to prevent touch voltage. Firstly, inspect the conduit regularly for damage or corrosion. Damage or corrosion can compromise the integrity of the bonding connection, which can increase the risk of touch voltage. Secondly, use insulated gloves when working on or near the conduit. Insulated gloves will protect you from electric shock if the conduit becomes energized. Thirdly, post warning signs to alert workers and the public to the potential hazards. Warning signs will help to prevent accidental contact with the conduit. In summary, bonding the conduit to the utility neutral is an important safety measure that can help to prevent touch voltage. It is important to follow proper installation practices and to take additional safety measures to minimize the risk of electric shock. The National Electrical Code, or NEC, provides comprehensive guidelines for electrical installations, including bonding and grounding requirements. Adhering to the NEC ensures safety and compliance with industry standards. Some relevant NEC sections include Article 250, which covers grounding and bonding, and Article 300, which addresses wiring methods. These articles provide detailed information on conductor sizing, installation methods, and equipment requirements for effective bonding and grounding. For example, NEC Section 250.102 specifies the sizing requirements for bonding jumpers and grounding electrode conductors. Section 250.104 outlines the requirements for bonding metal water piping systems and other metal structures. These requirements are designed to ensure that all metallic parts of an electrical system are properly bonded and grounded, minimizing the risk of electric shock and fire. When performing electrical work, it is crucial to consult the latest edition of the NEC and to follow all applicable requirements. Failure to comply with the NEC can result in serious injury or death, as well as property damage. In addition to the NEC, other industry standards and best practices can help to improve the safety and reliability of electrical systems. These include guidelines from organizations such as the Institute of Electrical and Electronics Engineers (IEE) and the National Fire Protection Association (NFPA). These organizations offer resources such as technical papers, training courses, and certification programs that can help electrical professionals stay up to date on the latest technologies and best practices. Proper bonding and grounding are essential for the safe and reliable operation of electrical systems. By following the NEC and other industry standards, electrical professionals can help to protect people and property from the hazards of electricity. In addition to the NEC and industry standards, it is important to have a thorough understanding of the principles of electricity. This includes knowledge of voltage, current, resistance, and impedance, as well as the behavior of electrical circuits under fault conditions. A strong foundation in electrical theory will enable you to properly design, install, and maintain electrical systems, ensuring their safety and reliability. When troubleshooting electrical problems, it is important to use appropriate test equipment and to follow safe work practices. This includes wearing appropriate personal protective equipment, such as insulated gloves and safety glasses, and energizing circuits before working on them. It is also important to have a clear understanding of the electrical system and to follow a systematic approach to troubleshooting. Begin by identifying the symptoms of the problem and then use test equipment to narrow down the cause. Once you have identified the cause, you can take corrective action to repair the problem. When working with high voltage systems, it is essential to have specialized training and to follow strict safety procedures. High voltage systems can be extremely dangerous, and even a small mistake can result in serious injury or death. Always de-energize high voltage circuits before working on them, and use appropriate test equipment to verify that the circuit is de-energized. In addition to the technical aspects of bonding and grounding, it is also important to consider the human factors. This includes providing adequate training for electrical workers, promoting a culture of safety, and ensuring that everyone understands the importance of following safe work practices. A strong safety culture can help to prevent accidents and injuries, and it can also improve the overall reliability of electrical systems. In conclusion, bonding and grounding are essential for the safe and reliable operation of electrical systems. By following the NEC and other industry standards, having a thorough understanding of the principles of electricity, using appropriate test equipment and safe work practices, and promoting a strong safety culture, electrical professionals can help to protect people and property from the hazards of electricity. For more detailed information, consult the latest edition of the National Electrical Code, specifically Article 250, which covers grounding and bonding requirements. Also, refer to IEE standards and NFPA publications for additional guidance on electrical safety best practices. Remember to always prioritize safety and seek guidance from qualified professionals when working with electrical systems. Ensure that all work is performed by licensed and experienced electricians who are familiar with the relevant codes and standards. Regular inspections and maintenance are crucial for identifying and addressing potential issues before they become hazardous. Implement a preventative maintenance program that includes periodic testing of grounding and bonding connections, as well as visual inspections of all electrical equipment. Keep detailed records of all inspections and maintenance activities. When upgrading or modifying existing electrical systems, always ensure that the new work complies with the latest edition of the NEC and other applicable standards. This may involve upgrading grounding and bonding systems to meet current requirements. Be sure to obtain all necessary permits and inspections before starting any electrical work. Educate workers and the public about the importance of electrical safety. Provide training on the hazards of electricity and the importance of following safe work practices. Post warning signs in areas where there is a risk of electric shock. Encourage people to report any electrical hazards they observe. By taking these steps, you can help to create a safer environment for everyone. The effectiveness of a grounding system can be compromised by various factors, including corrosion, loose connections, and improper installation. Regular inspections and testing are essential to ensure that the grounding system is functioning properly. Common tests include ground resistance testing, which measures the resistance between the grounding electrode and the earth, and continuity testing, which verifies that all bonding connections are intact. If the ground resistance is too high or if there are any discontinuities in the bonding connections, corrective action should be taken immediately. This may involve replacing corroded components, tightening loose connections, or reinstalling the grounding system according to the NEC requirements. When selecting grounding and bonding materials, it is important to choose materials that are compatible with the environment in which they will be used. For example, in corrosive environments, it may be necessary to use stainless steel or other corrosion-resistant materials. It is also important to ensure that all materials are listed and labeled by a recognized testing laboratory, such as Underwriters Laboratories or Intertek. This ensures that the materials have been tested and found to meet applicable safety standards. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges caused by lightning strikes, power line disturbances, or other events. SPD work by diverting excess voltage to ground, preventing it from damaging sensitive electronic components. SPD should be installed at the service entrance and at any point where sensitive equipment is connected to the electrical system. The selection of SPD should be based on the expected surge voltage and the sensitivity of the equipment being protected. Regular testing and maintenance of SPD are essential to ensure that they are functioning properly. Ground fault circuit interrupters, or GFCIs, are designed to protect people from electric shock. GFCIs work by monitoring the current flowing in the circuit and tripping the circuit breaker if there is a ground fault. GFCIs should be installed in areas where there is a high risk of electric shock, such as bathrooms, kitchens, and outdoor locations. Regular testing of GFCIs is essential to ensure that they are functioning properly. Arc fault circuit interrupters, or SIs, are designed to protect against fires caused by arcing faults. SIs work by detecting the unique characteristics of arcing faults and tripping the circuit breaker. SIs are required by the NEC in many locations, including bedrooms and living rooms. Regular testing of SIs is essential to ensure that they are functioning properly. Electrical safety is a shared responsibility. Everyone has a role to play in preventing electrical accidents and injuries. By following safe work practices, using appropriate test equipment, and promoting a culture of safety, we can all help to create a safer environment for ourselves and others. Remember to always consult with a qualified electrical professional if you have any questions or concerns about electrical safety. They can provide expert guidance and ensure that all electrical work is performed safely and in accordance with applicable codes and standards. Understanding electrical safety is an ongoing process. Stay informed about the latest technologies, codes, and standards, and continue to educate yourself and others about the importance of electrical safety. By working together, we can make a difference in preventing electrical accidents and injuries.